So the last part in this section is being able to use some of those laws that we use the axiomatic or procedural definitions to be able to prove a little bit longer sorts of problems involving set laws. So for instance, let's say we have a very basic example. A union B minus A is equal to A union B. So what we would do is we would take a look at the sheet with all the properties of sets, and the first thing you always want to try to do is you want to utilize any of the set complement laws, all right, or this, so the complement law or set difference law, excuse me. So in our first step, we're going to rewrite this as A union B intersect A complement. Okay. And that's by our set difference law. The next thing we're probably going to do is we're going to utilize a distributive property. And the reason we know to use a distributive property is because we look and we see that the two set operations are different from one another. If they were the same, we'd be able to use associative law. Okay, so I'm going to use the distributive property, and the distributive property is going to tell us that now we get A union B and A union A complement. Okay, so that's our distributive property. After the distributive property, we notice that we have A or A complement. So in this instance, we just take a look at our laws, and A union A complement becomes the universe. Okay, so this becomes A union B intersect, and for universe, what I'll do is I'll just designate it using this notation, because sometimes the U for union looks similar to the universe. Right? So again, that's a complement law. We take a look down the list of something that might have and universe, and if we look down the list and try to see that, it looks like the identity law is probably going to be the last one that we need for this. So that gives us A union B and that's by identity. And clearly that's what we needed. If we go back up to the top, we've shown that by utilizing these steps that it is equal to A union B. A second example, A set difference B, set difference C is equal to A set difference B union C. All right. So again, first thing that we always want to do is get rid of the set differences. So let's rewrite this as A intersect B complement quantity intersect C complement. Okay, that's just our set difference law. Noticing that both of the operators are the same, this time we can use the associative law, whereas in the previous example we had to utilize the distributive property. So we're going to rewrite this as A intersect B complement intersect C complement. Okay, that's just our associative. So that's the associative law. We notice that we have two complements and we have an intersect. So if we take a look at, I believe, our De Morgan's law, De Morgan's law says that we can kind of go backwards from this. And I don't want to say factor it, but we can rewrite it by almost factoring out the complement. So we can rewrite this as A intersect B union C quantity complement. Okay. Similar to De Morgan's law with logic, you take the complement out or you take the negation out, and then you flip the quantifier. In this case, you flip the operator. Okay, so this is De Morgan's law. And then finally, we notice that we have an intersect and we have a complement, so we can use the set difference law, except we can go backwards from that. Okay, so this time we're going to get A minus B union C, and that's our set difference. Right? And I believe that's what we needed to show. A minus B union C. So you can clearly see that both of these are equal to A minus B union C. So I would recommend that you try the very last problem that we have, see how far you can get with it, and then watch the video if you get stuck or if you think that you have a solution, so that way you can see the proper steps to go through and solve.